Good afternoon, everyone. Welcome back to network security. So on Monday, we look at FISTO cipher scheme, and then we look at a concrete implementation of FISTO cipher, and that is called data encryption standard, DES. So the take-home message last time was that for FISTO's cipher scheme to work, the only operations you need there is the exclusive OR operation and a substitute function. And the substitution could be anything. Okay, so it doesn't need to be invertible. So any function, so basically any function will make FISTO cipher scheme to be an encryption scheme. Okay, so that is the good part of it. So then for a concrete implementation, you keep the exclusive OR part, but then you think about ways to implement substitution function. Okay, and then you also need to implement round key generation. So that's what DES does. Okay, so DES use permutations and substitution boxes, which is also called S-boxes, to implement substitution and round key generation. So I asked you to finish up the video yourself last time. So now today we're going to look at a related topic that is a multiple DES. So before we start this video, so let me ask whether you have any question. All right, so then we're going to start the video. So stop me anytime if you have any question.
Multiple DES was used in the late 1990s, starting from late 1990s after brute force attacks were successful to crack DES. And the idea is to apply DES multiple times, either 2 times or 3 times. The underlying property of DES makes it possible. In other words, DES is not a group. Now, group is a mathematical concept, but basically what it means here is that there are no, for any, okay, so for any keys, K1 and K2, you apply DES twice, okay, you use K1 first, get a result, and apply DES using K2 first, and then using K1 by applying DES twice. And so you get a ciphertext. Then for any K1 and K2, and you cannot find any K such that applying DES once, you get the same ciphertext. So that means, in other words, for any K1, K2, and K, this inequality holds, okay? So by applying DES once on K is not going to be the same as applying DES twice on two different keys?
Even on the same key. So let's say you apply DES twice. So this E indicates a DES encryption. So you do it twice. Then it is not the same as you do it once. Okay, so this is not the same. So which makes sense that to improve to make your keys longer, you would typically come up with two different keys. So K1 and K2 then is a longer key. Then you apply them twice, you apply DES twice, and hopefully then you can get a stronger encryption to counter brute force attack.
So that you can use this result to do DES several times with the effect of having a much longer secret key. Okay, so for instance, so each secret key K2 is 50, K2 and K1 is 56 bits. So you combine them, it's 112 bits long. Okay, so the general idea is to take M keys and apply DES N times to get NDS/M. So this N and M may not be the same. So common ways to do it is 2DS/2. So you use two different keys and you apply DES twice. And you use two different keys, but you apply 3DS. You apply DES 3 times to get 3DS/2, or you get 3 keys and apply DES 3 times to get 3DS/3. Each time you would use each time you use a different key. But for 3DES, this is a normal way to apply DES. So you have two different keys, K1 and K2. Okay, you apply K1. So you use decryption on K1, and then you use encryption. Okay, this is encryption, this is the input. So you use encryption on K1, and then use decryption on K2, and use encryption on K1 again. So this also 3DES. Okay, the reason we want to do this is to make sure the ciphertext using single DES can also be can also be decrypted using 3DES/2. You just need to make that key using for single DES to be the key K1 and K2. So that way it is still applicable. Okay, so of course the other.
So let me just elaborate this a little bit. So what it means here is that let's say we're looking at 3DS/2. The reason we use this configuration is to make sure under this new scheme, it's still compatible to whatever that has been encrypted using the old scheme. In other words, using single DES. Right. So you think of this is what you have before. This is your encryption algorithm E. That's what you have before, and you have a message, and then you encrypt it, and then it becomes SIG. now assuming that everything now we are going to do the decryption, we will have this new algorithm. So this is 3DES/2. So the reason for this configuration then is that if we set, now it takes two keys, K1 and K2. So if we set it for this thing, I want to decrypt it. You can just make K1 equal K2. Then you can use this algorithm. So let's just say this is the algorithm, the new algorithm. So this is E prime K, right? It takes two, but we are just using the same key as K. So that same key K as this K1 and K2. So then we know this decryption is DK. Now under this new algorithm, EK and DK. So that is M, right? So this is 3DES, but with this two keys, but these two keys we set equal. So this cancel. So this is equal to DK. Oh, the input here is a C, sorry. So this input here is C. So this is decryption, this is encryption, so they cancel. So we got DKC, then this is M. Okay, so that's the reason why we want this configuration, so that it can be used to decrypt ciphertext that is generated using a single DES.
Combinations of E and D, encryption and decryption, are just as secure, but then the encryption using single DES may no longer be applicable for this other combinations. All right, so using two keys to extend the key length to 112 bits would make DES much more secure against brute force attacks. But as we said, 3DES/2 was a common way to go using this combination of encryption and decryption. But if you apply DES twice using two different keys, then the brute force attack may still be doable, even though it is more difficult than before, but it's not that much more difficult because there is a technique called the meet in the middle attack. Okay, so now let me open up a whiteboard so I can give you a better idea. Get a whiteboard. Okay. So 2DS, okay, /2 would mean that you apply encryption twice using two different keys and get C. So what I want to find is K1 and K2. So to find K1 and K2 using this encryption from the attacker's point of view. So we hope that K1 and K2 can substantially increase the brute force attack difficulty because both of them. So you're combining these two keys, you get 112-bit key. So if you do brute force, you will do in the worst case, hopefully you have to do 2 to the 112's power many different trials, and in order to get K1 and K2, right? So you get K1, that's 56 bits, and then you try another one that's 56 K1 and K2, and then using these two and see whether you can break your systems. So in other words, you have a known pair.
Professor?
Yeah.
Like,
are these K1 and K2 the same as the Ks that were generated from for the previous algorithm to create the different XORs, or are these different Ks?
No, the different keys, but same algorithm.
Okay.
You just apply them. Okay, so well, you want them to be different in order to make your key lengths to be long, right?
So you're still, but we're only generating a couple here where we needed to generate more than a couple previously, correct?
What do you mean?
So
for previously the round key. Now, okay, so now
it was K. It was like K to the N before, where it seems like it's only a couple here.
What do you mean K to the N before?
And granted, this was more of a what's the word? Example more than anything else, but we were saying we are going to generate K to the N keys to properly XOR this.
Okay. So now the logic is this: if you use exclusive OR,
yeah.
Okay, in order to make it secure, you want a one-time pad because each key can only be used once.
Yes.
That's for that algorithm. Of course, that is not practical.
Mm-hmm.
We cannot use that to encrypt your message for network communications.
Mm-hmm.
Right. So then, of course, then we have to come up with a new algorithm. And this is the new algorithm. DES is a new algorithm, encryption algorithm. And each key can be reused.
Okay.
So then in order to apply DES, you just need one key. Okay, just need one key, and then you could have, as we said, that it has 16 rounds. So that means you got to have 16 subkeys, but those subkeys are generated from K. Okay, so that's 56 bits long. Would that make sense?
Okay, yeah.
Yeah, but then this is subject to brute force attack because you can just try all possible keys. So you get
all possible combinations,
yeah, 2 to the 56 many. And let's say you have, somehow you get a pair, you have MC. So this pair means a known ciphertext, right? So you got M, I know C is a ciphertext of M. So you try all of these keys and apply them either on K, no, this is all of them, either on C to see whether it's equal to M, or you can use encryption, try to see whether it's equal. If one of these keys make it equal, that means you break the system, right? That makes sense?
Yes.
All right. So that has been done in the late, well, I'll say in the mid 1990s. So people build special machine to break the system. And later on, they don't even need a special machine. Instead, they build a distributed algorithm, right? So by using all these idle machines on the network. So each machine will do some checking, right? So as you can see that it can be done. So then, of course, the one immediate solution would be, okay, I want to have a longer keys. So that's the reason we use a multiple DES. The longer keys means I apply DES more than once on different keys. Okay, so
Okay.
so that we said that we have a 3 combination that's common. So 3DS/2, 3DS/3. Oh, by the way, this is still used today. Okay, so they are still secure. But then we also have another combination. You apply DES twice using 2 different keys. So what we are trying to say here is that this is not secure. It's still subject to brute force attack in the sense that by brute force attack, you may want to try all possible combinations. So this is this many. But using meet in the middle attack, I don't need this. I don't need to try this many. Okay, I will try more than this, but not much more. That makes sense. That's the roadmap.
Yes.
Yeah. Okay.
Like a DES. So let's say you have a known ciphertext, so you get known. So I try all possible K1 and K2, then I see whether I get this equality. So if we do, then probably we get that case. So you got to see this many times. But then, of course, if a single key is 2 to the 56, so there is a huge difference. But using meet in the middle attack, we can reduce this complexity tremendously. We can reduce the complexity from 2 to the 112's power to 2 to the 58's power. So 2 to the 58 is not much bigger than 2 to the 56. Okay. Now let's see how we can do it. So so let's say I have a known pair. So this is a known pair. So that means I can get D K2 on C should be equal to E K1 of M. So what I'm going to do in this meet in the middle attack is I'm going to apply. So I get all 2 to the 56 many keys. Right, so let's get K1, K2, until K2 to the 56. So I get this many keys. For each key, I'm going to compute. So this is a key. I'm going to compute both encryption and decryption. So this is E, K on M. This is D, K on C. Now you know M, you know C, so I can run this. So then I will get so let me call this Okay, so so in order to make it easier, let's call, by doing this encryption, I get x1 using k1. Using k2, I got x2. And then I got x2 to the 56. So for this, I apply these many keys on M. I got these possible outcomes, all of these outcomes. And similarly, for this, I'm going to call it y1, y2, and then y sub 2 to the 56 power. Now, here, so this means, now this is equalities. Okay, because of this, we get this. We just don't know which K1 and K2 would be. So then I'm going to compare. Okay, so let's say if K2, if K1, maybe it will have to have something that is equal. So if X1 is equal to Yi, or Y2 somewhere is equal to Xj, then, so this is corresponding to this is K2, corresponding to this is Kj. Then in this case, K2, Kj, now, so I want to, so when I do this, so these K1 and K2 are not the same as this K1 and K2, so let me make that clearer. So I'm going to say two keys. One is K, the other one is K prime. Okay, so that way, so this is K prime, this is K. So then for this K2, so that is a candidate for K prime K. So this is a candidate. So if this is unique, then we are done. We found K, K prime and K. If unique, then we found K prime and K, which is K2 is K prime, Kj is K. But the situation would be that there are so many such candidates, okay? But there might be many candidates, such candidates. So that means we don't know which one it is. All right, so then let's assume I have another known pair. Assume is assume another known pair. Let's call it M prime, C prime. Okay, so now for each candidate, key pair K prime K. Now each candidate, there may be so many. Then I'll apply this on this string again. So I'm going to do is I do mk on m prime. Also, this is E. Do it again. This should be equal to dk prime on c prime. Using the same thing, okay? Using the same table. But then what we need to do is to find out how many such pairs available, how many candidates. Right? So of course it won't be or any pair will be candidates. Of course it will be much smaller. And then so the key pairs, so the number of such candidate pair much smaller. So I apply on another known pair, and I am going also to get the same thing, also to get candidates. Okay, so so we get candidates and then get new candidates. Let's call this star, 4 star. Okay, if so we can show with probability greater than 1, this is unique. So such candidates is unique with probability greater than 1. I'm sorry, cannot be greater than 1, of course, close to 1. So 1 minus, close, very close to 1. Very close to 1. Hence, with a large probability, we find this pairs of keys, okay, with 2 known pairs M and C. All right, so the complexity, okay, is at most originally you get 2 to the 56, but you do encryption and decryption, so which means you do it 2 times. And then the second round, so this is the first round. The second round, let's say you have how many pairs? Let's call this K pairs. And we already use K, so let's call use a different number. Let's say N pairs. Okay, so this time you do N for each pair. You want to do this many you want to do this many encryption, and you want to do this many decryption. So that's 2 times N. If N, let's say in the worst case, it will just be, so this is in the worst case, right? So N will just be 2 to the 56. So that will be 2 times 2 times 2 to the 56 is 57. So this is 2 to the 58. Okay. So the complexity is much lower, and then you have a large probability to find these keys. So now let's move back. to find out. So remember here, we look at this. Okay, so this is how many pairs in the first round, how many pair of candidate keys. So this is the first round. So remember, to begin with, there will be this many keys, but then each block is 64, right? So some of the block under those keys will be the same. So then the candidate pairs is at most 2 to the 112's power divided by 2 to the 64, because that's how many different blocks you can have. So that's 2 to the 48. So that means n is 2 to the 48. Okay, in the previous slide. So then you have this many key pairs. For this key pair, you apply on the second known plain text and ciphertext. So this is a second round. So then you get 2 to the 48 divided by 2 to the 64. Again, 2 to the 64 is how many possible blocks you can have. So that is 2 to the negative 16th. So the possibility of finding k and k prime is then 1 minus 2 to the negative 16. So this is a very high. So this is a very, very high number. All right. So then we know that 2DS/2 is not secure because of this reason. Brute force attack may still be doable. So then, of course, a common way is either 3DS2 or 3DS/3. So this is considered secure.
Okay, so now we move on to advanced encryption standard. So that is the one that's commonly used today.
Okay, finally, we are going to look at advanced encryption standard, AES. So this is the current data encryption standard. It was, excuse me. Okay, so it was devised by 3 cryptographers or mathematicians. Okay, it was initially called the Ringdale. Okay, and so this algorithm was selected to be the AES in 2001. Okay, so AES AES is not following Feistel's cipher scheme. Okay, so it uses a different scheme, but it still has multiple rounds and using multiple round keys. but it is not simply based on exclusive OR and substitution function F. Instead, it is based on finite field operations. So as we mentioned earlier, so this is a byte level. Okay, so this is a byte level operation. So the operations are operated on bytes, which is 8-bit long, and it's a finite field. It's called Galva field, GF 2 to the 8. This was first studied by a French mathematician called Galva. Okay, that was Galva. So the things here is each byte is represented by a polynomial of degree 7. So this is a byte. So this is represented by a polynomial. So this is a unique representation. E1x E0. And you can then define multiplication. You can then define addition. So addition is the same exclusive OR. So this, and subtraction is the same. Okay. And then you can define multiplication and inverse of multiplication. So this is division. So division is harder, which has to do something with has to do with something called irreducible polynomials. But as I said, we don't need to worry about how these are done. We just need to take granted when we look at these operations that we know that there is a strong mass behind these operations. Okay, so that is one thing. The second is that instead of a fixed key length, AES supports 3 different lengths. One is 128 bits, the other one is 192 bits. The last one is 256 bits long. So for anything that requires strong confidentiality, you can then use 256 bits. For normal applications, 128 bits probably would be good enough, for instance, for wireless communication. Okay, so in chapter 6, we are going to talk about this. So we're going to come back again. And then the block size is 16 bytes, so that's 128 bits long. And so instead of represented a block using a linear string, we are going to represent it using a 4x4 square matrix. Okay, and to represent this 16 bytes, so 4x4 16. So so this is a 4x4. So we got A00, A01, A02, A03, and then the The last row is A30, A31, A32, and A33. So this is 4 by 4. Each of these AIJ is a byte, so you got 16 bytes. So that is your block. So it uses 4 simple operations, okay, on this state matrix. So this is called a state matrix. And we use 4 operations to operate on this state matrix. So let me now remove this and then move on to the next slide. Okay, takes a while. Here. Okay, so these 4 simple operations are the following. Substitute bytes, we call it SUB. Shift rows, called SHR. Mix columns, MIC, and add round keys, ARK, ARC. Make ARC, okay, sub, shift, make, and ARC. Okay, so substitute bytes is a nonlinear operation based on a defined substitution box. Now, remember we said that these operations are on this Galva field to the X power. So because this is field, we can have inversion. So we can define a invertible substitution box. Okay. So this is used to resist cryptanalysis attacks and other mathematical attacks. Okay. And shift rows is simple, it's a linear operation. And this is used for producing diffusion. Mixed columns is also elementary operation, and it is used for producing diffusion. And then we have these add round keys, which is has something to do with keys. So this is used to produce confusion, and this is linear. Mixed columns this mixed column operation uses quite a bit of finite field operations. Okay, so here is a diagram. So plain text comes in. You first generate, okay, we use AES 1 to 8 as an example. So this is AES 1 to 8. So it has 10 rounds, and it would need to use 11 keys, subkeys. Okay. All right, so we got 11 subkeys. And so your plain text comes in, you first confuse, you first use the first subkey to produce some kind of confusion, and then the output of this is going to be the input of round 1. So round 1 is a sequence of sub, shift, make, and arc. So repeat this, okay, until round 9. So round 9 is still the same number, same sequence of operations. But in round 10, the operations are different. So then you get a ciphertext. Okay, so decryption is not completely symmetrical. Okay, so ciphertext comes in, the same thing. You use the 11th key, but then here the ordering of these operations are inverse shift, inverse sub, arc. Inverse arc is the same as arc, so because it's exclusive OR. And then inverse make. So it's not in the same orders as encryption. So you do the same sequence of operations for 9 rounds, and then in the last round, you have inverse shift, inverse sub, and then arc, which is also not exactly the same order of the encryption. So this is at a higher level. This is a higher level view of AES. So now let me remove. Okay. Okay, so AES box, S-Box, AES S-Box is a 16 by 16 matrix built from operations over finite field GF of 2 to the 8th. So what it does is it is a permutation of all 256 elements. Okay, so each element and its index are represented by 2 hexadecimal digits. Okay. So now let me do annotation a little bit. Okay, so this is 16 by 16 Xbox. Okay, so so we got 16 rows and 16 columns. So then each of these is a 4-bit number. And we are going to use a hexadecimal hex to represent it. Same here. For each row, for each column is also a 4-bit number. Okay, 16. And then for each element, because you got 256 elements, so each element is a byte. So this is a byte, and then it's going to be represented by 2 hex number. Okay, the first 4 bits is 1 hex number. The second 4 bits is another hex number. So that's what this matrix is. So this matrix, let's call it S. So S is invertible. Is invertible. Okay, it has an inverse. So this matrix has inverse. Okay, so what is this by substitution function? Okay, so we let W be, now I start with B0, okay, B7 be a byte. So we define a by substitution as, function as follows. So we take the first, so this will be my row number, and then this will be my column number. So Sij from this matrix, okay, so this is 16 by 16, that's S. So that element is the substitution, that's the value of this input. So this is the input. Okay, the output is Sij. The element at the ith row and the jth column. So, if we call this input W, then that's what this means. So it has inverse, so the inverse on W gets, sorry. So I should say the inverse on Sij, it gets you back to W. So that's what we have. Okay. So now let me see if I want to erase all this marking using undo. Okay. Not as convenient. So let me just do this. Move down. Move down. Okay. Then let's see add round keys. I'm sorry, let's see key generations, round key generations. Oh, so looks like this, so this should be, so this, so this should be this, this should be this. So this operation is actually defines, so this is a number. Okay, so this is represented by a polynomial. Let's call it f of x. Okay, so this number is f of x. That's a polynomial. These are the coefficients of that polynomial. And this m really defines x times f of x. And this small mj defines the operation of x to the j's power. Okay, so so we don't need to worry about the underlying mass to come up with this form, but what we just need to take is to take it as granted. So if B7 is 0, it is a left shift, right? So this is left shift. Otherwise, if B7 is 1, it will be left shift first and then exclusive OR this. So this is a irreducible polynomial. That means so these are coefficients of a reducible polynomial. What that is x fourth power plus x cubed plus x plus 1. Okay, so this is a, so we just take it as granted. So again, for this Sj, you apply this capital M because this x multiplies itself for j's times. So you get this multiplication, right? So if j is 0, that's just number 1 because x0 is 1. If j is 1, it's just x itself. So this is number 1. So this is x. Otherwise, it will be equal to x times x to the j minus 1. So that's why you use capital M. So that is for x times, let me use this symbol, x to the j minus 1. Okay, so that's how you define these two basic, how you got these two basic operations. So what we want to see here is how these subkey, round keys are generated. So we first define this TW comma J, and W is a byte. Okay. I'm sorry. No, it's not a byte. It's a, yeah. W2 is a byte, but your input, your W is a 4 bytes long string. So we call this W1, W2, W3, W4. Actually, I have it here. Okay, so what you want to do is you apply S substitution box on S2. And then you apply small m, or so exclusive OR of small m of J minus 1. So this J is right here. So, and then you concatenate S of W3, S of W4, and S of W1. So that's what this T is. Okay, so just to make it fairly complicated, but the execution itself is efficient. But when you want to do analysis, it would be very hard to do. So now let me erase this to move on to the next slide. Okay, now we put these things together to generate round keys. Okay, so this is a 32-bit. So our key is 128 bits long. So let me put it right here. So we have our key, 128 bits long. So we can divide it. We can divide it into 4 segments. The first 32 bits is the first segment. And then the second 32 bits, the third, and the fourth. Okay, so this then is going to be, as you can see here, so this will be W0, W1, W2, W3. So from now on, I'm going to define WI because I want 11. I want 11. So this is already the first key. So then I want 10 more keys. So that means I want 44 many such WI. So that gives me 10 keys. 40 many, not 40, 40 many. Altogether is 44, but this already, 4 is already counted here. So for this is how it is defined. So WI is equal to W. If I is divisible by 4, then this WI minus 4 exclusive OR this function T. So now this is where it is used. And this is I divided by 4. Otherwise, you just exclusive OR the WI minus WI minus 4 exclusive OR WI minus 1. So that's how it is defined. So finally, we then have the 11 round keys defined in this way. So let me now remove this. We can move on to the next slide. Okay. So add round keys, just exclusive OR. Okay, so simple, byte-wise exclusive OR. And as we know, exclusive OR, the inverse of exclusive OR is exclusive OR itself. Okay, so hence this is arc inverse is arc itself. Okay, substitution, substitute bytes. We just apply the substitution function S on each element is inverse, applies the inverse of S. So this is also easy to understand. And then we have this, because this is inverse, so we have this sub inverse of A gets A itself. Likewise, sub inverse on A, then you get A back. So shift rows is pretty straightforward. So what you do is you shift each row starting from row 0, left shift for 0 times. So starting from row 0, or if you think of this as the first row, then you shift it for 0 times. Okay, so if this is the second row, you shift it 1 time, left circular shift. So that's how you get this result. So likewise, the inverse will be the right shift, right? So circular right shift again, you shift it back. So that is simple. Okay, mixed columns would be the most difficult, most complex operation. So, but each operation here we have already defined. So we already defined the capital M, and then the rest of it is exclusive OR. It's just the positions you apply this capital M would be different. So this is for the first row, second row, third and fourth row, right? So this is how you do. So these J is from 0 to 3. All right, and the inverse. The inverse, now this is a nonlinear operation, obviously. So the inverse, you got to say this is n cube. And so don't worry about the mass here. We just take it as granted. So then the encryption and decryption is as follows. So, so this is just the encryption. Let me do some annotation a little bit. Okay, so this is the first subkey you use, and then you repeat the same sequence of operation for 9 rounds. So substitution byte, shift rows, mix columns, and add round keys. And the last round, round 10, is different. Decryption, you also, in the similar fashion, but it's not symmetrical. Okay, so so the operation are all inverse, but then it's not the same sequence. So for 9 rounds, it applies the same sequence. So not the same sequence as encryption, but for decryption, it repeats 9 times of the same sequence of operation, and the last round is different. Okay. Here is a correctness proof of decryption again. We use mathematical induction. The proof is fairly straightforward. So what we want to show here is that for any I from 1 to 10, we want to have CI, which is equal to shift rows substitute some bytes, and then A sub 11 minus I. Okay, so once we have this, then we can show that C11 is indeed A0. Okay. Okay, so assuming, now let's say we're assuming this is true, then let me do an annotation. Then we have, because this is what we want to show for decryption to work. So we know by definition, C11 is, the last one is at wrong key, substitution by inverse, shift row inverse, and on C10 and K0, because we use, when we apply these wrong keys, we use the inverse order. So now C10 is equal to, assuming this is true, we know this is equal to shift row, and then substitute bytes, A11 minus 10, C10, okay, so then that's A1. So let me put it here, A1. And then we close these parentheses, we got 3 more. And then add wrong keys. So that's equal to this. Okay, so these two cancel each other out. After that, subs cancel each other out. After that, what we are getting, so sorry, we don't have this. Okay, let me rewrite it again. Okay, so I'm going to say these are at wrong keys. So we're gonna put this in first. So this is a sub C10 at wrong keys. And then this is sub inverse, shift inverse. I'm sorry, C10 is equal to shift rows, which is, and then substitute bytes, and then this is A1. 1, 2, 3, exclusive or K0. Okay, so let's cancel each other. And then we got sub A sub 1. And let's cancel each other. So we got A sub 1, K0. Okay. And then A sub 1 is equal to A1 is from A0 in the first round, so that's A1. So this is A1. Okay, so then we know these cancel. So we get A0, okay? The same thing, exclusive or itself. K0 exclusive or itself is 0, okay? So that is why, okay, if we prove this, then we can show the correctness of AES decryption. So now let's see.
Okay, so the time is up here, so we're going to continue this topic. Yeah, this is one of the most difficult chapter in the book. So we spend a little bit more time, so that we have a better understanding of these building blocks for network security. Since we haven't finished up this lecture and one more lecture, so I'm going to again change the due date of discussion board and the quiz to Wednesday. Okay, so any questions for me?
No.
All right. So then I'll see you next week. Bye-bye.
Bye.
Have a good one.